Sweet. So we're going to be talking about a couple new comonads today. Before I get started, actually, was there anyone who didn't make it to the previous lectures? That's totally fine. Yeah, we got one, got two. Okay, that's good to know. I'm not going to go over too much of the previous stuff, but hopefully you'll be able to keep up. We're going to just look at what a comonad is again. Hopefully this doesn't look completely foreign to you since yesterday. But we talked about how a comonad has three operations that kind of define the class, right? And these all relate to operations on the monad type class, but they do very different things. So remember, we have the extract method. We talked about queries and how basically you have anything with this sort of structure that can pull something out of a context as being a query. And this is kind of the null query. It just gets the thing that's in focus in the data structure. So for a stream, it was the first element. For the store comonad, it was whichever one the index referred to, right? Just get me something, something that makes sense. We also talked about duplicate, which is basically you have some structure like a stream and whatever elements you have in there, and we want to add an additional layer of structure to that. So we're going to nest streams within the stream, and it has to kind of match up with our intuition of what that means for a stream. So in the case of a stream, each stream that was now lifted up from the original started that stream at the element which matched the position of the original stream, right? So that one's a little bit clearer to see with graphics, but we'll get there. And then extend, basically it takes something that matches this query type and some structure, which we can query over. Come on in, guys. And it extends it along the entire thing. Anyone see a spot to sit nearby? I think we have one at the end there. Any room on the couch? It's a little tight. I'm not going to be using my chair. Someone can steal this if they want it. Maybe we'll throw it over by the door. Or maybe there's room over here. Just watch the camera there if you're... Yeah, no problem. Throw one over here. Good stuff. Okay, so extend basically allows us to take a query, which normally would compress down the entire structure into a single element, but it actually magically allows us to extend it along the entire structure and maintain the structure itself. So we saw for a stream how this would basically allow us to take a stream operation, like take three elements from the root of the stream and produce a list. And if we can do that in one spot, it would actually run it over the entire stream and say, oh, for each slot on the list, these are the next three elements of the stream. And for this one, these are the next three elements, and so on. So we're going to move on and we're going to see how these apply to some other comonads today. So we're going to take a look at the env comonad. This is co of some other monad. Does anyone want to guess which? Reader, exactly, yeah. So it turns out we have an environment here, and this represents the co-reader. Before I get started, I just want to thank Wire for, this is the company I work for. We do end-to-end encrypted messaging, and they're helping me be here. And we're hiring Haskell devs and DevOps positions in Berlin. So if you're interested at all, either come talk to me after or hit up wire.com/jobs. Cool. So we have an environment. So let's talk about kind of the intuition of what this data type is and what it can do and how it all works. So we talked about before kind of these slots and views idea. Env is very simple. It has a single slot. There's only one spot that you can put something in this structure. Stream, we talked about, had infinitely many slots. This just has one. It's much simpler. And we talked about how you can view the structure from many different viewpoints. Well, if you only have one slot, you only have one view. It's really kind of boring. There's only one spot that you can actually see the structure. And it's reader monad-ish. Reader monad is all about the idea of having some context for your calculations, right? If you haven't heard of reader monad, that's fine. It just is basically a way of implicitly passing information around. Env is the opposite of that, so we kind of still are passing information, but we have the information explicitly. We have a concrete object of that information, and we can kind of mess with it as we like, whereas reader, we're kind of waiting for one to be provided. Do we have questions about that? I love questions. I'd love to hear some questions. Yeah, huh? Oh yeah, that's the whole rest of the talk. Cool, great. Let's go on to the examples. Okay, so before we can actually start building things, let's take a look at what it looks like. The data definition, the type is exactly the same as the actual data definition. So it's a type which has an environment and it has an A. So this is isomorphic to tuple. It's just got two things. That's fine. And we're just going to derive all these nice things. We have a functor over the A. Okay. Well, I'm just going to implement Comonad on screen here because it's really, really not so difficult. If we want to get an A from our structure of 1A, well, we just take the A out. Okay, no problem. If we want to duplicate, well, it's a little bit trickier. You just put one inside the other, and away you go. So we've nested our context within the other, and this passes all of those laws we talked about. If you duplicate and then extract, well, of course, you end up exactly where you started. And extend. Okay, so given a computation which reduces an environment down to a single value, if we have an environment of A's, how do we get to an environment of B's? Well, we copy the environment and then we run the function on it. So immutable values, it's no problem. We still keep an E around for the future, but we can pass one to this function. Okay, so what sort of queries can we do? With store, we talked about the peek query, and we can kind of look around in this context, and we can see what's nearby. With the stream, we could query by looking downstream and see what other elements we have. Comonad env, just like reader, has ask. It's the same name for the same concept, but of course, everything is a little bit flipped on its head. Ask just says, well, if I have an environment of E's, I want to get the E out. That's all I care about. So it's actually equivalent to first, basically, if this were a tuple. We just take the thing out. And in this case, if we have a concrete example, we've got an environment with the integer 42 stored, and the A value, hello, we just get the 42. No problem. We'll see what this is useful for in a second. We also have asks, which is the same as reader version. If you haven't seen that before, what it does is not only does it get the E out, but it allows you to do a quick modification to that E before it's returned, or maybe select a subset of it or some transformation of it. It's just a convenience thing. It doesn't actually give us any additional power. You can implement asks in terms of ask and vice versa. But in this case, let's say we have actually a tuple in our environment. We can ask for the first part of that tuple. It will first get the environment, then get the first part, and it'll get us that value out. We can do the same with the second. This all okay? Everybody following along? Cool? Great. All right, so real example. Kind of real. Small real example. We have some settings. So we're going to use these for building some sort of text formatting pipeline-y thing. Okay? And we want to set it up so that basically all of our functions, they can use these settings to decide how they're going to do their operations. And maybe we want to run it again with a different set of settings. And, we're going to do some text padding, and we're going to decide how much we want to pad that. So we have an integer saying, oh, well, pad all of my values on the edges with this much margin. The maximum size of our string when we're done, and which character we want to pad with. So yes, this is a random set of things, which was auspiciously chosen for this example, which happens to need this. So we can write a custom query here, which from an environment of settings can actually get an integer, which represents the, oh, sorry, this should be a character. Yes, this should be a character. That's a typo. Okay, so given an environment of settings, we can get a character out. And, this looks silly, right? It's just a function which takes some stuff and gets something out, but this still matches the signature of a query. So it's still important, and this means that we can extend it. We can run it on our Comonad. Okay? And notice, different than reader, we can actually get this out. So we can run this and we can get this out. If it was a reader version, we would still be stuck inside a reader over the environment. Okay? So let's create a real version of this settings context. So there's this function exposed by the Comonads library. It's actually just an alias for the data constructor. And it takes two arguments. It takes the environment and the value you want to store inside. So we're going to pass it some settings. I'm going to say I want three 3 paddings on each side, and maximum length of 5, and we're going to pad with stars for now. Now, like all comonads, we need to store something in here. We must always have a value in scope, and this doesn't necessarily need to have any relationship to the environment at all. This is just kind of the value we're working on at the time, and it's going to change as we go through our pipeline and through our calculation. So we can ask for which character is in our context, and we get it. We run the query on the environment, we get something out. Okay, and of course we can just use asks to get something out of the environment that way. Any questions so far on kind of how this works? It's really not so interesting, but it's going to come in handy when we hit Comonad transformers. Okay, cool. So let's do something a little bit more interesting. I can see a lot of board stares. Let's see what we can do if we start to mix some of these things together. So we're going to write a function, which is happens to be a query here, where we accept some comonadic environment value, and we're saying we want it to have a list of things inside it. We don't really care a list of what, but this operation cares about, you know, limiting the size, so we're going to say we want a list. And we can use this let binding to say, okay, well, from the environment, I want to ask for the length, the maximum length that we can possibly have, passing W into this query. And then I'm going to use W again to extract the actual list that we're working on, and then run, you know, I'm only going to take up to the maximum length from that list. So we're actually passing this W into multiple spots because we can run multiple queries on it and get more than one piece of information, combine all of that together into our resultant value, and then get that out the other side. Okay, any questions on this query and how we're using asks and how we're passing the W around all over the place? Cool. So W is this environment, which has a list in it. Now, it turns out strings are also lists. So if we're working over just the basic string type, this function will work for that as well. All right, so we have hello world, and we've set up this max length of 5. So if we run truncate on it, it will look up the 5, and then take only the first 5 characters, and it will output this. Now notice we're not extending over this truncate, so it does actually reduce the structure, but we'll see what happens if we start to get a little more creative. Okay, let's write another function. So again, you can see we have a query, right? We're going from some context over a string to a new string, and we're going to pass in the W, and we say, well, okay, let's figure out what padding we want to have. Again, we're just going to ask for how much padding. We're going to ask for which character we want to pad with, and then we can just replicate that character by the padding amount. So this is going to give us, you know, if we have 5 of the stars, then we have 5 stars to pad with. And remember, extract is always just going to get the value we're currently working on. And so I can run this whole thing, and I can put the padding on the front, have the thing, put the padding on the back, and we've wrapped our currently working value with padding on both sides. Let's see what that actually looks like. Okay, pretty simple. And we can start to imagine, well, okay, those stars made it where they need to be. If we start to mess with this environment, even though we're not explicitly passing like all of these weird environment values in here, they do show up in the resulting calculation. So very much like reader, you spin all of your calculations together and then you provide a value at the end. Env is the opposite. You provide a value up front and it will thread it through all the calculations. Okay. So now we have all of these individual queries, but we need to stream them together into some sort of pipeline workflow. So the environment comonad, unlike all of the other ones we've looked at, like the stream and the store comonad, can't actually change the environment using a query. It only has a single slot, so it can't really move slots around. It can mutate the value inside it, but of course you could just do that with, you know, fmap, or you could, but then you wouldn't get to look at the actual value inside. Sorry, the environment. But what we can do is we can chain these pipelines together in an interesting way. So we're going to remember this Kleisli compose arrow here, or Kleisli compose, depending, where it takes 2 queries, and it goes from the input of the first to the output of the second. So this is like a composition operator, but with some W's threaded through it. And it implements this using that extend. Okay, questions about everything we've been going on? Anyone? No? Okay. Cool. So we can chain multiple queries into a pipeline. So if we have this truncate thing that shrinks the string that we're working on down, and we have this pad thing, which can explode it up, well, we can truncate the string and then pad it, and we get this hello with the stars on both sides. And of course, if we change which environment we pass in, it's going to do different things. It's just kind of implicit in the pipeline. Now note that order does matter for this, right? So if we pad first and then we truncate, well, it's going to run those in order, of course. So we end up adding the padding and then only taking 5, which includes the padding. There is a function, however, which lets us alter the environment. This is similar to local in Reader, of course, where you can contextually, in a very small portion of your block, you can change the reader monad to have some different behavior. We can do the same with the environment. So it allows us to, given some function which takes the environment and produces a new one of some new type, we can take an environment context around some value, and we can strip off the old environment, run it through this function, and put it in this new one. There should be an A here. Got cut off, I guess. Okay, but you'll notice that this type signature isn't a query, right? It should have an A here. It goes from a contextual value to another contextual value, which means we can't thread it through these pipeline combinators like you normally would. But what we can do is we know that each of these queries is being passed a full object. Trunk takes a full object, and then it duplicates and extends, and then passes in a full object here. So if we want, before we put our query, remember composition goes right to left in these individual blocks. So we can set the padding character to a different value and then run the pad and then continue. Now, because this only changes the environment here and pad consumes the environment and then throws it away, this local is actually local. It only works immediately before pad, and then it reverts back to the original environment as it continues down the pipeline. So the ability that gives us is first we're going to pad with underscores here, and then we're going to pad with the original settings in our context, which is going to be the stars. Okay, questions about this pipeline thing? Yeah. Yes, it's defined specifically for env. So it has a different type, but the notions and the ideas are the same, so they gave them the same names. That's right, yeah. But this local, it operates over the env comonad specifically. Great. Any other questions? Yeah? Mm-hmm.
So far I struggle to see a difference in use cases between reader and env, but I guess we are yet to get there, right?
Right, so the primary use case that I would see for Comonad env is that it's really handy when you're not wanting to work in a monadic context and you just want to have real values that you can pass around and edit and mutate and whatever. It's kind of more an object-oriented approach where you say, oh, I have this object which has all of the context I need to perform some operation, and then you can think of these queries as being methods on that object, which can access all of the fields of the object and make some change. And when you extend, it's as though you're doing a mutation because it calculates the new value and sets it back into that A slot, right? So it's kind of similar to that. The other part of it is with Comonads transformers. You can use this to pretty nice effect. It stacks with the other Comonad transformers properly. So you can put this anywhere in the transformer stack, just like you can put reader anywhere in the reader stack. Yeah, yeah, that's fine. Mm-hmm. Any more? No? Okay. So speaking about how we're going to thread all this stuff through, someone asked about CODO notation the other day. This isn't CODO notation. I want to be clear about that. CODO notation is a different thing that's in a different paper, and I'm honestly not super familiar with it. It unfortunately didn't pick up too much popularity because Comonads are unfortunately not as popular as monads. Maybe someday it'll make it into the language, but this is my do notation that I use for Comonads. I haven't seen this anywhere else, but I find it really useful. So in all of these computations that we've seen before, we're passing in this W that we're acting over, right? This contextual thing, and we want to run some queries over it. But you'll notice every time we've used it, we have to pass a W in here and run the query. We have to pass a W in here, and we run this query. And we end up building up these big let blocks where we're just passing in the same thing because we want to keep querying over the same context. There's actually a lot of situations with the store monad that we would end up doing the same thing. So what I like to do is I actually use the reader do notation when I'm working with the env comonad. This is going to be a little bit confusing if you haven't seen this before. If you don't get it, that's totally fine. I think it's a neat little snippet when you're working with comonads that this is using the function monad. Okay? Have any of you, who here has seen the function monad before? Yeah? Okay, so a good amount. It's actually the exact same as the reader monad. So if you know the reader monad, this is the same thing, except it just doesn't have a new type around it. So rather than saying reader env setting string of string, we use the function arrow instead. And there is an instance of this in base, so this should just work. So we're implicitly passing in this environment. And what that ends up doing is it will basically insert that W for us on the right of every line of the do notation. And
so you're basically passing in an end in a reader?
Yes. Yes, I am. And, damn it all, it works. So this is what I like to use. Yeah, maybe there's a reason I haven't seen this posted anywhere. I don't know. But I think it's quite convenient, and it reads like kind of nicely, right? So we're querying over our structure, and we say, oh, give me the padding amount, and give me the padding characters. And it just knows where to get these from. So the way the reader monad works and the function monad works is basically each line where we use this arrow notation has to accept one additional parameter, which is the thing that we're working on. So in this case, it'll accept this environment on the right, and it's equivalent to these ones up here. Okay? People mostly following this weird hack? Yeah? Okay, cool. Let's
Just, I didn't want to start a framework here. Like, how can your friend do things that is like making things clearer?
Well, that's a good question. I don't use this at work, so I'm so far the only person who's seen these slides. Maybe we can have a flame war afterwards about it, and you can tell me it's not clear.
I know that the function monad is actually there.
Yeah, of course. So, yeah.
I just wanted to find it in production code and fail.
You wanted to see it fail. Okay.
I just wonder.
Yeah. So one thing that is people talk about is it's very confusing for beginners. I completely agree with that. Definitely agree. And the reason that I think it's confusing is because we have the reader monad, right? And so most people use that because it is clear. And so basically what I'm getting at is that the things that make things clear in Haskell, most of Haskell is confusing, but we have idioms, right? We have these patterns. And if a pattern gets popular enough, then the confusion starts to go away because, well, it's one of those things that you learn and it's in all of these posts and stuff like that. So maybe if comonads start to get more popular, this will become an idiom, and then people will use it, and it won't be confusing. But until then, maybe you should stick with this one. And I'm not saying which one to use. I'm just saying this is an option. Cool. So we can see in the original where we have a let block where we extract, well, now we can extract from this implicit value. And in cases where we don't use the environment, well, we have to use a let block so that it's not trying to force that in there where it doesn't belong. And lastly, we can return instead of using the in. Okay, moving on.
Question?
Yeah.
How exactly, I'm not sure if I'm like spacing something, but how exactly do you handle extend? Like when you
Right, yes. So that's where these do notation blocks are for building up a single query. And then you use the pipeline notation to extend in between queries. Yeah, that's right. You can actually, there is one example where we do an inline extend in one of these do blocks. But that'll be in the Comonaid transformer section. Cool. And just because, yeah, you're going to hate this part, but I just like to see how code golfy Haskell can get for fun. Don't worry about this. If you don't understand it, it's really not important. But we can abuse the do notation even further and use the applicative syntax to run all of these through, and it'll combine the queries for us if you squint enough. And you can get even worse if you really just want to torture GHC. So this is fun, not recommended. Okay, so that's the reader monad. So not honestly too much to it, right? It can kind of just thread an environment through, but it's going to come in handy later. Any last questions about the environment? Great. Cool. Let's move on. So we're going to talk about traced. All right. So traced is co-writer. We just did co-reader. We're going to dive into co-writer here. Now, who here is familiar with writer and kind of how it works? Cool. The writer monad itself isn't actually used terribly often because of performance issues, but people are working hard to kind of sort out better ways of doing that, and it's popular in a lot of logging frameworks. But that's not what we're talking about today. So this is co-writer. So writer is concerned with monoids, where you can basically have some value that you keep appending onto. So for a writer monad, that's often used for logging frameworks and that sort of idea, where you have an implicit log and you want to add a new log message. You want to add a new log message. You don't care what the current state of the log messages are, you just want to say, I want to add a new one. So this is a function version, where we have a function here which takes a single argument, which is a monoid, and returns some A. Now, can anyone think of why it's important that our argument to this function be a monoid?
With our writer, so that you can use things together and write successive things.
Yep, that's one thing that we're definitely going to use this for. So one other really important rule, it has to do with extract. Yeah, got a thought? Yes, that's also true. But in this case, for a Comonad, we have this law that we have to be able to implement extract, which means given some structure, we need to get an A out. Now, if this was just some arbitrary argument, where are we going to get that from, right? We can't just make up some arbitrary argument. But if we have a monoid, we have a way to pull one out of thin air and say, well, we're going to use mempty, the identity element, and we can pass that in at any time. And so if you just want to get the result, we can force this function to run by giving it the empty value. Okay, here's the implementation. Not so tough. And I'll mention, I guess, the monoid constraint is on the Comonad class, right? So that we don't like to put constraints on constructors. We just put it on the Comonad class itself the Comonad instance for traced. Okay. So this is a function where the argument is a monoid. So if we look at this closely, we'll notice this thing itself is a query, right? Like the function is part of our type here. This thing takes some value and returns some result. So if we treat reader of M as our W, as our context, we have an A inside. And we can think of it as that sort of query operation. So here are some examples of queries which have a monoid as the argument. So here we've got sum, which takes a structure filled with integers and returns an integer. How does this relate to Comonads? Well, we'll get there. Length is another one, right? It takes some monoid, right? So lists are the free monoid. Everything that's in a list is a monoid, right? Like it lifts things into a monoid. And we have these other kind of more interesting ones. Map has a monoid instance, and if we have some set of things and we want to calculate, you know, the weight of the items in our backpack, we can do that. This isn't terribly interesting. But we can talk about how traced is very similar to the store comonad. So in the store comonad, we had a function which backed our data structure, but we always had to keep that argument with us, right? Because we need to be able to run the function at any time. In this case, it's the same thing. We have this function, very similar to the store comonad, but instead of keeping that value with us, we actually bake it into the whole idea of this structure by using the monoid. So we can run it at any time using the monoid, but what we'll see is if we want to add context to that function call, we can bake it into the function using composition. So we can actually kind of apply a monoid into the function and then forget that we did so until a later point. That's really confusing. Let's see what it looks like. Let's see here. So, like I said, this is only a comonad when the argument is a monoid. That's a requirement. Let's see what we can do with one of these things. Okay. So, extract. Well, like I said, if we want to just run this function, we can pull a value out of nowhere with mempty, and away we go. We get the result. Great. So what does that look like? Well, if we're dealing with this function, sum, which takes a list of integers, which is a monoid, we can build a traced comonad out of it. And we now have this traced which accepts a list of integers and returns an integer. And if we extract it, it applies sum with the empty element, the empty list, and we just get out a 0. Okay? So that's the really basic kind of thing, and it does match our comonad intuition that extract is like the null query. It just runs it. Do we have questions about this? Besides, how is this useful? We're getting there. Yeah?
Do we get away with using default? I mean, it's a lot less type class and stuff, but I guess do we use appends?
Yes. Coming up. Great question. Okay. We have another query called trace. Okay? Trace applies the function to an argument. So trace takes the argument that we want to apply to this function and the function itself wrapped in traced and just applies it. So really this looks dumb. It's a little bit simple, but there's a reason. So we can trace 1, 2, 3 with this adder comonad that we created out of the sum function, and it'll run sum over the list of 1, 2, 3. Away we go. Okay, now extend. This is the only thing that's really interesting about having a function that's a comonad is we can extend it. Otherwise, we're just running functions all day long, and you didn't come here for that. So extending takes an argument, extending with trace, takes the argument that you would normally run the function with, and it bakes it into a new version of that function implicitly. So it's just always there. So let's see what that actually looks like here. So if we extend over our original adder, which has just the empty list as its identity element, we extend it through a trace. And remember, normally trace would just run the function and get a value out, but now we're extending. So it runs the function and gets a value out, but keeps it inside a larger function, okay? Which still accepts the monoid as an argument. It's very strange. But somehow we've done something with this 1, 2, 3. Now, what have we done with it? Well, we'll see just in a little bit, but you had the right intuition there, Paul. We are baking it into the function such that the new function accepts an argument and it appends the one that we've already baked in on the front of the new argument, and then runs the internal function with that. So we're creating layers of functions where each time we make a new layer, we're adding some more context to the argument. We're adding some more context as we go all the way down, okay? And so we can see that if we trace this, we get this new thing, which looks like this. When we run it, we pass in mempty, it implicitly adds the thing that we baked in, and then it runs the function and we get 6. Here, we're using this adder prime here, and we're going to trace again. So now this says, okay, oh, there should be an mempty in here. So it should be Oh no, because we're tracing. So this will run it with this 10, which is implicitly appended to the front of all existing baked-in arguments, and it extracts. This is a little tricky. Do we have some questions?
Can you rewind 2 or 3 slides back? And, yeah.
Okay, is there something you're looking for?
I need to rewind.
Okay. Anyone else feeling a little bit fuzzy on this one? Yeah? Okay, yeah, we got a couple. Okay, I think let's maybe take a little aside here, and let's look at the implementation. Okay. Oh, sorry about that. Okay. So, is that fitting on the screen? Yeah, mostly. Okay. So, let's see how we duplicate. So, here we are duplicating our traced, which means we have to nest another one inside it somehow. Okay? So we have this traced function. This f is the function. So in our case, this is sum, right? And it takes a list of integers and it returns an integer. And we have to return a new traced with a traced inside it. That's a requirement of duplicate. And so we built this new function, which still takes an argument. And on the inner one, we can see that we're first appending to the argument of the inner function, and then passing it to the original function. So we're explicitly saying, I'm going to eventually take a new argument, but before I run the original function that I'm wrapping, I want to pass it this, I want to append onto the argument.
Isn't there some performance consideration, because depending on the monoid, you may have to replicate the function calls inside of it, several on each call?
Sure. So we're building up funcs here, and they can potentially get quite large. That's a possibility. But it also gives us a lot of laziness, because everything is delayed computation. That means we can actually deal with infinitely large data structures and not worry about it, and we'll only actually compute the funcs that we need. So potentially it's bad for memory or computation. That's a price we pay. And if you have a real problem with it, then maybe we can optimize an individual case. Is this helping a little bit? It's still weird, right? Hopefully we have the intuition, even if we don't quite understand the implementation, that every time we trace, we're going to just kind of add this additional context to the function. Okay? Let's see if more examples will help. Okay.
Can you go back to the other definition yet again?
This one? Okay. These slides are also actually published in the repo right now, so if I do go a little bit too fast for some of you, you can pull up the PDFs. They're available for you there. Cool. Okay, so let's keep on baking some stuff in. So we're baking these arguments into new functions, which will apply them and combine them and all of this stuff. Oh, I had it right here. What do you know? Okay, so even if we apply this inner function, it still remembers the argument. That's kind of part of it now. And each time we extend, we add a new argument to the front. That's important. In the case of sum, the results of sum are, they don't depend on the ordering of the argument. But if they do, we'll see what happens here. So we're going to use this concat function now, which takes a list of strings and combines them into a single string. So we've just used that as our function. We can log a message here and say, I'm going to first add hello to our context, and then I'm going to add world to our context. And I'm combining these queries together using that query composition, Kleisli arrow. Okay, well, if we run it, we forgot that each time we add one, it actually prepends. And so we've ended up with this beautiful thing here. Not quite what we wanted. So that's something we need to keep in mind. One way to solve that is actually just to use dual from data.monoid, and it flips all of your monoid operations and it sorts it out. But okay. Do we have specific questions? Cool. Okay, so the intuition here is tricky. This is a tough one. We have to go through more examples, because this is very abstract stuff. Your position, when we're talking about a traced comonad, right? We still like to think of these as spaces that we can move around in. Still a good intuition, just a little bit tougher. Our position is implicit. We've lost our map. We don't know where we are, okay? We don't have that value that we have in store to look at and say, oh, this is where I'm going to extract. But there is still a position. We are still somewhere. We just don't know where it is. We can't talk about our current position. And so because we don't know exactly where we are, we can only move about our space relative to where we are, okay? And the way that we do that is by giving movements in our monoid. So not all of them really make sense with that intuition, but in the case of the sum example, we can move our sum higher by appending some more list elements that are positive, and we can move our sum lower by appending some list elements that are negative. And they move us around. With strings, right, you can kind of append onto the string, and that's going to move us to a different value that's eventually going to be extracted. That's a tougher one. But we can look nearby. And what that means is if we think about peak, or peaks rather, from store, where we can say, oh, I don't care where we are, I just want to look 2 to the right or 2 to the left, or at a position that matches this. We can do relative movements that way and take a peek at what the sum of our current value would be if I added these numbers to the list. But we can't remove things from the list. We can only ever add more with append. Okay. And extending through that trace moves you to that position by adding to that argument, or bakes those function arguments in. So whichever of these two things I've talked about is a little bit more intuitive, use that in your head. They seem at odds with each other. They both work, kind of. I'm sorry, this is getting tricky, okay? Who's feeling a little bit iffy on this one? Okay, maybe we'll end up spending some more time on this. But I think this example might help. So we are going to compute the derivative of a function using the traced comonad. Okay? Going to take you back to high school math for a second. And we can talk about how a derivative is actually a contextual calculation. So if you think about a function's derivative, it's the idea of the slope of the function at a given point. Well, if you only think about an individual point, there's no notion of slope, right? A single point is not a plane. You need multiple things to look at to decide what your slope is. So in a function, if you can only look at the y value for a given x, it's impossible to compute the derivative, right? You don't know what the surrounding values are. But the derivative at a given point can be estimated. We're not going to do any linear algebra. I'm not going to do any symbolic derivation. We're going to estimate it as best we can using the nearby values of our function. So when I say nearby, if you have an x, well, if you look 1 to the right of that x and 1 to the left of that x, and you can kind of get an idea of what the slope might be. And as that distance gets smaller, you get a better and better and better idea. Okay, so don't worry if this doesn't make sense. This is how you can estimate slope at a discrete position. So we say, to get the derivative of f, we can accept an x for our derivative function, and we look at what f of x plus 1 is, and we look at what f of x minus 1 is, and we find the difference between those two, okay? So in this case, if our y at this spot is here and our y at this spot is here, well, we can find the difference between the two. And then we can divide that by the entire distance that we're spanning. So if we look 1 to the left, 1 to the right, then the distance that we're spanning is 2. And so we need to kind of average that down to get the actual, it's rise over run, right? Slope equals rise over run. This is approximately what we're doing. Who is following on the derivative calculations? Yeah? Okay, great, good. You have good high school teachers. Better than me, at least. Okay, so we have this function. Doesn't really matter what it is. Happens to estimate the square root of 16. So you can see at 4, we hit 0, right? So it's finding the roots, and that's the square root of 16. But that's not important. We just have a function. Okay? Cool. Okay, we're going to pick a spot on this function to talk about. But remember, all of the stuff that we do from this point on, we actually don't need to know that we're at x equals 2. They're all relative movements. So we're going to pick this spot here in the corner. And we can consider, like I said, the x values 1 to the left and 1 to the right. Okay? Now, given that we have some function as our context of our comonad, we can look 1 to the left or 1 to the right. We just can't say, oh, jump to x equals 5. But if we have an x, we can say, let's look 1 to the left or 1 to the right. And if we can do that, we can calculate that estimated slope, which isn't perfect, but it's close. And then we can compute the entire derivative, which of a parabola like this is just a nice straight line. Okay. Whoa, this is going to be tricky. We can get through this. Okay. So we need a function which accepts a monoid. So I'm going to take our function that we had, x squared minus 16, and I'm going to inject the argument into a monoid. So this function now takes a sum of our x. So our x is now a monoid, where we can move it higher or we can move it lower by m-appending negative or positive numbers. Okay? So if I have x equals 1 and I m-append x equals 2, I end up at x equals 3. If I have x equals 1 and I m-append minus 2, then I end up at minus 1. So I can move higher or lower without even knowing where I currently am. Does that relative movement kind of start to make a little bit more sense? Okay. So we still can't ask which x we're at, but it turns out it doesn't matter. We don't need it. We can say that we can take any x and we can compute this function, and then we can wrap it in traced. So
should that be a new type wrapper? The traced at the bottom line, f equals traced?
No, so traced is a function that's exported from the library, which is basically an alias, but similar to the MTL implementations, they implement the non-Comonad transformer version in terms of trace T identity. So this lifts it into trace T identity. So yeah, you can just use these lowercase versions of the constructors and it does the lifting for you.
Sorry, question.
Yep.
So is the basically being able to move around
Yeah.
comes from the fact that you're building up the computations without running them, right? Without the fact you can move without knowing where you are means that you must not be running the computations. You must be delaying the actual computation, right?
Exactly. So that's a great point. How can we possibly calculate a y value if we don't even know where we are, right? Well, what we can say is we're going to implicitly calculate all y values and run our queries on every possible position using our good friend extend, such that later we can pick one of those positions and see what is actually there if we had run everything everywhere all the way through the pipeline. And so that's where it's really handy that when we extend, we stay underneath a function. It's all still lazy, it's all still wrapped in a function, and eventually that will be forced when we try to see a result. Okay, good stuff. Does this definition make sense? How we've turned our function graph into a mathematic function and then wrapped that in our comonad. Okay, so implicitly we know that our x here equals 0, because if we haven't added anything or subtract or moved, we're going to start off at the identity element. The identity element for sum is going to be 0, it's a double. Okay? So we know that we're at 0, but the functions themselves don't. And if we extract, well, of course we get that. So it was x squared minus 16. 0 squared minus 16 is minus 16. Great. Okay, if we do sum of 2, well, 2 squared is 4 last I checked. Minus 16 gets us negative 12. And we can do kind of these things. We can still use our function like a normal function. And because we start off at 0, 0 plus any of these arguments is going to end up at the argument itself, which is convenient, but kind of a happenstance. How much time do we have here? Okay, yeah, we're almost done. But we're going to continue on this and go into Comonad transformers after the break, I think. Yeah, there we go. Good stuff.